First, there is some terminology, some basic definitions that we are going to talk. Then we are going to talk about some basic rules, of radiation, basic rules of radiation. Okay, and then the third part will be view factor. I think it is view factor, or I think there is some other thing after laws. Yeah, after laws there are basically rules. One second. Okay, so there is heat radiation laws, radiation heat transfer laws, Stephen Boltzmann's law, Planck's law, Wien's displacement law. Then there are few rules, some 3 or 4 rules: symmetric rule, reciprocity rule, addition rule, summation rule, and addition rule is same. And then we come to view factor, the most important part. View factor, the most important part. So today's lecture is divided into 4 parts. Then tomorrow we will do heat transfer through non-black bodies and black bodies. Okay, chalo, let's start. Okay, so we will be starting from the first term, which is terminology. Some basic terms, some important terms that are important from radiation point of view. You see, look, whenever, let's say you have this body, this is a surface, this is a surface. Okay, now let's say some radiation is incident on it. This is called as incident radiation, incident or incidence, incident radiation, or rays, you can say. Okay, and let us call it Q naught. It is the total incident radiation on the body, total incident radiation on the body. Okay, now some part of this radiation will be absorbed. Some part of this radiation will be absorbed in the body, which, let's say, QA. It is the absorbed radiation. Some part will be absorbed. Okay, let me call it as absorbed radiation. Now some part of this will be reflected back, reflected, QR. This is reflected, and some part will be transmitted out. Transmitted means it is not been absorbed. It is basically gone out. For this object was transparent for it. Okay, so this is Q dot tau. This is transmitted. Okay, so part of the radiation, if when thermal radiation is incident on a surface, part of it may be reflected, part of it may be absorbed, and part of it may be transmitted. Now the terms that are defined are, the first is absorptivity. Absorptivity, it is the fraction of radiations absorbed by the body. Okay, fraction of what? The total incident radiation. Okay, so absorptivity is defined as Q absorbed upon Q dot A. Okay, I'm sorry, Q dot O. Okay, yes, Q dot A by Q dot O. Yes, it is a fraction that is absorbed by the body out of the total incident radiation. And now, of course, you will know what will be reflexivity. It will be the fraction that is reflected out of the total incident radiation. Yes, and transmissivity will be the part that is transmitted out of the body. Okay, clear? Now, if I do energy conservation, so these radiations will be coming with some energy, right? So energy in will be equal to energy out if this body is in thermal equilibrium. If this, because for all practical applications, you want your body to be in thermal equilibrium. Okay, so there is no absorbed. Okay, I mean there is no stored energy. Okay, so energy in will be equal to energy out now, or plus stored as well. I'm sorry. Energy in is equals to energy out plus if something is absorbed. Okay, what is coming in? Q dot naught is coming in QA plus QR plus Q tau. Okay. Now, what should I do? Let me write it in this way. Let me divide everything by Q naught. So what will I get? Plus Q dot R plus Q dot naught plus Q dot tau by Q naught is equals to 1. I have divided everything by Q naught, right? And now what is this? Absorptivity, what is this? Reflectivity, what is this? Transmissivity is equals to 1. The summation of absorptivity, reflexivity, and transmissivity is equals to 1. Okay, and of course, all the values of absorptivity, reflexivity, and transmittivity will vary from 0 to 1. 0 to 1. For example, if it is a black body, it can absorb everything. It can absorb everything. Okay, so if the body is absorbing everything, then it is alpha is equals to 1. If the black body is radiating everything, then it is reflexivity is equals to 1. Or any body, or if like if the body is transmitting everything, then it will be transmissivity is equals to 1. Now opaque body is a body that does not transmit anything, then transmissivity will be 0. Okay, so transmittivity will, or any absorptivity, reflexivity, or transmissivity will vary between 0 to 1. Either it can be 0, or it can be 1, or it can be any number between 0 and 1. Okay, if fraction is absorbed, then it is somewhere between 0 and 1. If nothing is absorbed, that means absorptivity is 0. If everything is absorbed, then absorptivity is equals to 1. Okay na? Clear? Similarly for reflexivity and transmissivity. Okay, chalo. Let us move on to the definitions. Okay, so 3 things we have defined: absorptivity, reflexivity, transmissivity. Fourth is black body. Black body. So it absorbs all the radiant energy reaching its surface from all the directions and all the wavelength as well. Okay, so it can absorb any radiation irrespective of its direction and wavelength. Okay, so by energy conservation, this is what we know already. This is what we know already. Now I am saying it is absorbing everything. It is absorbing everything. That means for black body, it is already written here. For black body, absorptivity is equals to 1. Then by this definition of A, reflexivity, I'm sorry, this is reflexivity and transmissivity will be 0. Will be 0. Okay? Yes, black body is a diffuse emitter. Diffuse we are going to talk about in some time. Diffuse means uniform in all directions. If this is coming, it is going to diffuse, it is going to emit everything in irrespective of direction. Whatever direction is there, uniform distribution. Okay, so this is diffuse. This is diffuse. Yes, independent of direction. Yes. Okay, we will talk in some time. Anyway, we have talked that earlier as well in the introduction part. Okay, chalo. Transparent. What do we know about transparent? Means it is transmitting everything, transmitting all the radiations that are coming on the surface of the body. It is transmitting everything. Okay, transparent means it is transmitting everything. It is not absorbing, it is not reflecting. It is transparent for the incident radiation. So of course transmissivity is equals to 1, and of course by definition of A, absorptivity and reflexivity will be equal to 0. And as I told you already, for opaque body, its transmittivity is equals to 0 and therefore this is equals to 1. ठीक है, ये definitions you need to remember. These are very simple definitions that you need to remember. ठीक है, and I think this we already read in basic physics also in our 11th and 12th. ठीक है, चलो. So few definitions of it. We all know it is a perfect emitter and absorber. It can also absorb based upon the type of surface. It can also absorb that is entering inside the body, or it can emit also. Okay, I gave you the example also earlier how it is emitting and how it is absorbing all the radiations that is entering inside the black body. Okay, at a specified temperature and wavelength, radiation emitted by the black body is maximum. At any temperature or wavelength, it can emit maximum radiations compared to any real body. ठीक है, and its radiation does not depend on the direction. That is called as diffuse radiation. It is called as diffuse. ठीक है, and I have already told you by the diagram as well. Now, a black body may appear black in color or may not be a black body. Okay, sometimes you may see that the color of the body is black, but it may not be a black body. Okay, it is black body in terms of wavelength. Okay, in terms of wavelength. So for example, sun, cavity with a tiny hole opening, cosmic microwave background, furnace valve, etc. There's an example of black body. Perfect black body is the ideal body which is taken as reference. It is on. Yes, snow. No, snow. Yes, snow is a black body. Snow is a black body. Yes, very nice. Okay, snow is a black body. Chalo. So let us come to gray body. Now look, it is perfect. Now black body is a body that can absorb or emit radiations irrespective of direction and wavelength. I'm sorry, irrespective of temperature and wavelength. Whatever temperature, whatever wavelength, it does not matter. Temperature and wavelength. Okay, but of course we cannot get this type of body. In order to the radiations to be diffused, it should be a perfectly fine surface that you cannot ever achieve. Okay, so let's compare to a more realistic, in fact that is also not real, but more realistic surface that is called as gray body. Now as I said, that is independent. Black body is independent of temperature, or black body radiation is independent of temperature and wavelength. Now for gray body, its emissions, its radiations are independent of wavelength only. Properties are independent of wavelength. Now it is an imperfect black body. Why? Because it depends on the temperature. Okay, it absorbs certain fixed percentage of radiation if they are coming at a fixed percentage of radiation. Okay, at a particular temperature, and absorptivity is constant. Gray body again is a hypothetical body like black body. It is more realistic than black body, but it is also not a real body. Okay, a gray body is defined such that the monochromatic emissivity of the body, emissivity is this. We will read the definitions also later on, but emissivity we show it by this symbol. Okay, so emissivity of a gray body is not a function of wavelength. It is independent of wavelength. So emissivity at wavelength 1 is equals to emissivity of wavelength 2. It is not a function of wavelength. Whatever wavelength comes. Okay. It is independent. Monochromatic emissivity of a body is independent of wavelength. What is monochromatic emissivity? It is emission radiated by the real body and by the black body. Is defined as the ratio of the emitted radiation at a specific wavelength and temperature to the emitted radiations from a black body at the same wavelength and temperature. Okay, so emission radiation energy by a real body divided by radiation energy from a black body. Okay, so if I need to find out energy emitted by a real body, so I have to multiply it with the emissivity and then the radiation emitted by the black body. So for black body, emissivity कितना होता है black body के लिए? How much is the I have written it already. For black body, emissivity is equals to 1. Yes, very nice. Sean and Sahil, correct. Yes. ठीक है. Next is white body or specular body. Okay. So I have already drawn this diagram. Now this is black body. Black body means diffuse radiations. You have diffuse radiations. Specular body is when the angle of incident is equals to angle of reflection. Okay, so for white body, reflexivity is equals to 1. Reflexivity is equals to 1. Alpha and tau, absorptivity and transmissivity is equals to 0. Okay, a body that reflects all the incident thermal radiations is called as absolute white body. Absolute white body. Now, regular radiations or specular radiations means angle of incident is equals to angle of reflection with respect to normal plane. So the light, the radiations will be reflected at the same angle as it is coming, as it is incident on the surface. Okay, with respect to the normal. So this is the normal. So I incident radiation is equals to reflected angle. Okay. Now, in a diffuse radiation, incident beam is uniformly reflected in all direction. That is for black body. That is for black body. It is independent of direction. Okay, most of the engineering materials have rough surface, and these rough surfaces give diffused reflection. Okay, so they kind of provide not absolute diffused, but they kind of provide you diffuse radiations. Okay, they cannot provide you specular radiations. Chalo. Next is spectral emissive power. It is also called as monochromatic emissive power. Monochromatic emissive power. Okay, so what does it mean? The rate of energy emission per unit area at a particular wavelength. At a particular wavelength is termed as the. So it is specular. When we talk about spectral emissive power, we are talking about only one wavelength. Only one. So emission, you always show it by capital E. Energy emission, show it by capital E. Okay, of, let us not write B here. B is for black body. We are talking about any general body. Any general body. Okay, and we are talking about spectral or monochromatic. When we talk about spectral or monochromatic means we are only talking about one particular wavelength. So it is equals to, it is shown by this, and it is given by sigma t to the power 4. We will see this equation later on in Stephen Boltzmann's law. Stephen Boltzmann's law. But it is given by this. It is given by this. Now, and if this is something that you need to find. Now, this is for black body. Okay. This is for black body. For real body, you need to multiply it by E lambda B or emissivity, Stephen Boltzmann's constant, t to the power 4. And the unit is what? Can you tell me what is the unit of this? What is the unit of energy emissions? Yes, very nice. The whole thing is energy emissions per unit area. Very nice. Watt per meter square. Now, if I need to find out heat transfer, I need to multiply it by area. I need to multiply it by area. So if you ask me to calculate heat transfer, then it is emissivity, absorptivity, area, t to the power 4. This is how I can calculate heat transfer in watts. Okay. Now it is only at a particular wavelength. It is only at a particular wavelength. If I need to calculate the total, heat transfer, then I will need to do the integration for the entire wavelength of spectral emissive power. For total emissive power, I need to do an integration along all the wavelength that it is receiving. Okay, clear? Chalo, chalo. So these are few definitions that I need to do. Now last is emissivity. I have already showed you the ratio of radiant energy emitted by any surface, by a real surface, to that emitted by a black body at the same temperature. At the same temperature, okay. And it is given by, as I already told you, radiation emitted by a real body and radiation emitted by a black body. Okay, and for black body, emissivity is equals to 1 for black body. For non-black body, it is less than 1, not equal to 1, less than 1. Okay, if it is a perfectly, like it is very, very close to black body, then you can assume, okay, 1, but it is less than 1 for real bodies or non-black bodies. Okay, chalo. So this is the first part of our lecture, which is terminology. Now we will move to the second part, which is the laws of heat transfer. Laws of heat transfer. Clear? Let us move on. Chalo, chalo. Now this is the second part, which is radiation heat transfer laws. Radiation heat transfer law. The first law is Planck's law. Planck's law. Now, what does it say? Planck's law says that emitted wavelength distribution of black body radiation. It is the law that tells you wavelength distribution of black body. And in simple terms, it actually tells you that the radiation emitted is a function of wavelength and temperature. This is basically the definition of Planck's law, that the emission radiation, whatever is radiating from the surface, is a function of wavelength and temperature. Is a function of wavelength and temperature. Okay. Now let us see what is happening if we are talking about at a constant temperature. We are only working at a constant temperature, at a specific temperature. So let us take this T to 2000 Kelvin. Let us take this 2000, one temperature, specific temperature. Now, let us say you are here, you are at this point, 1, okay, at some wavelength. Now, if you are increasing your wavelength, then your emissive power is also increasing. Your emissive power is also increasing, right? You are going in this direction, your emissive power is increasing. And then it reaches to a maximum. You keep increasing your wavelength. You are going in this direction. So first of all, it is going to increase. It will reach to a maxima, EB lambda maximum. And after that, it will start reducing. Okay, so it is about one specific temperature. When I'm talking about a single temperature, one specific temperature. So as I am increasing lambda, first of all, the emission radiations are increasing, or emissive power is increasing. It is reaching to a maximum, and then it is decreasing. Okay. Now, if I am increasing the temperature or decreasing temperature, let's say I am decreasing temperature T1. If I have decreased the temperature, okay, so you see, same thing will happen. Of course, same thing will happen. That first of all, emissive power is going to increase, which will reach to maximum, and then decrease. But at lower temperature, the peak will shift to right. The peak will shift to right. Is it clear? At lower temperature, the peak will shift to right. Okay. So I can say it in the other way. If the temperature is high, then peak will shift to left. That means shorter wavelength. Right? So what can I conclude? That higher temperatures emit radiations at shorter wavelength. Higher temperatures emit radiations at shorter wavelength. Can I say this? Or not? Higher the temperature, shorter the wavelength. Isn't it? Lower the temperature, larger the wavelength. So If temperature increases, peak of curve shift to the left. That means towards the shorter wavelength. At high temperature, large fraction of radiations are emitted at shorter wavelength. Okay. Now it is actually telling you about the radiation energy that is only for a particular wavelength, only for a particular wavelength, not to the entire range, not to the entire range of wavelength. Okay, there is also a, Planck actually gave a big equation for radiation energy. It gave you a equation, but we do not need that equation. It gave you some equation in terms of wavelength and temperature, but we do not need that equation anyway. Okay, now the limitation with this law is it only talks about the radiation at a particular wavelength. If we keep heating, the wavelength emitted by the black body decreases. Black body does not matter, no. It is independent of temperature and wavelength. Yeah, normal body, yes. If its temperature will increase, it will radiate energy at shorter wavelength. Okay, chalo. So the problem with this is it only talks about radiation at a particular wavelength. Only talks about radiation at a particular wavelength. So then comes Stephen Boltzmann's law. It basically whatever we give you in Planck's law, we will integrate it through the entire wavelength. We will integrate it to the entire wavelength. Okay, so it gives you the radiation emitted through the entire range of wavelength. This law states, now it law states that the total hemispherical, why do we say hemispherical? Because a body can only radiate energy in hemispherical direction. Okay, it can only radiate in this, it cannot radiate below. So it cannot radiate here, it cannot do that. Okay, it will only radiate in the horizontal, in the hemispherical way. Okay, so total hemispherical emissive power of a black body is directly proportional to the fourth power of the absolute temperature. So total emissive power of a black body is proportional to the fourth power of the absolute temperature. And also, so this is what Stephen Boltzmann's law gives you. Very, 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 very important point here is that even look, anyway, when single temperatures you get, you have to put temperature in Kelvin. But even if a temperature difference, you put that in Kelvin. You put that in Kelvin here, even if you get temperature difference. Okay. So always, whenever you are applying Stephen Boltzmann's law, in fact, I will say whenever you talk about radiation, you try to put your temperature in absolute temperature in Kelvin. Okay. So if I remove the proportionality sign, I introduce a Stephen Boltzmann's constant whose value is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay. Now, in the exam, it is expected that you remember this value, Stephen Boltzmann's constant. Sometimes they give, sometimes they don't, but they expect you to remember this value. Okay, so write it every time you do a question, write it down, or even if you're not doing, because very few times you are going to use this value, but still you need to remember this value. Okay, now this is for a black body, and by definition it is given for a black body. By definition of Stephen Boltzmann's, it is given, look, it is given for a black body. Now, let's say I know for a black body I know the radiations emitted by a black body by using Stephen Boltzmann's law, if I know the temperature. But how will I know the real body emissive power? I will know it by multiplying it by emissivity. multiplying it by emissivity of that surface, of that body. Okay. And when I talk about total emissive power, so this is emissive radiations or emissive power per unit area. This is emissive power per unit area. But when you need emissive power, then you need to emissive power, you need to multiply it by area. You need to multiply it by area. Clear? Clear till now? Chalo. These are the things that you have to read it out. Nothing else. There are not much concepts here. Okay, most of the things are definitions, laws that you need to study, that you need to read it out loud and know what they are trying to say. Okay, chalo. Because you see from here, I get a equation in the look. Planck's law gives you that it is a function of lambda and t. It is telling you emissive power per unit area is a function of lambda and t, but it is only talking about at a particular wavelength. Then Stephen Boltzmann's law basically integrated it and told you the total emissive power irrespective or for all the wavelength in the range of entire wavelength. Okay, and it gave you this equation. It gave you a very important equation. This equation you can say, and this equation also, and this equation also. All the this is the basic equation. Everything is based on what we have discussed earlier. Okay, chalo. Now Kirchhoff's law. Kirchhoff's law. It is the relationship between emissivity and absorptivity. So it tells you that for a real body in thermal equilibrium with its surrounding, its emissivity is equals to its absorptivity. Simple definition, which we are going to use later on as well. So it's a very important conclusion that you need to remember. Okay. Now, how did it come? So basically, let's say you have a black body, you have a non-black body. Okay. So whenever a non-black body is radiating, let's say it is radiating emissive power per unit area E to the black body. Now, of course, black body will absorb everything. It will absorb everything, right? Now, okay. Look, it is some temperature T and it is also temperature T dash. So, of course, both the body will be reflecting and both the body will be absorbing, right? Now, how much they are absorbing, how much they are reflecting depends upon their temperature. If higher temperature is there, they will be reflecting more energy emitted. Okay. So now it is whatever it is radiating, black body is absorbing everything. Now black body is also radiating something. Let's say it is radiating EB. Emission radiated by black body EB. Right? Do you need to do it? Okay, I'll write. Let's say radiation emitted by non-black body is E. Now that is the radiation absorbed by the black body as well. Okay. Now radiation emitted by black body. Black body is how much? EB. Okay. Now radiation absorbed. Whatever is incident on the body, on the non-black body, radiation absorbed by non-black body. How much? It will depend upon its absorptivity. It will depend upon its absorptivity. Okay. So absorptivity, EB, whatever the absorptivity, it will absorb it, right? Now, based upon its reflexivity, based upon its, so you see, look, alpha plus rho plus tau is equals to 1. Now it is a opaque body. It is a opaque body. So transmissivity is equals to 0. Now alpha plus rho is equals to 1. Now what is rho? 1 minus alpha. 1 minus alpha. Okay. So radiations emitted by non-black body from this absorbed, how much it will going to reflect? Emissivity, EB, emissivity of EB, right? Whatever the reflexivity will be there, it is going to reflect that, right? Yes. Okay. So this part is absorbed. You see, out of this total, you see, this is the surface. Out of this total, EB, some part is absorbed. How much? Alpha EB. And some part is reflected. How much? Rho EB. Okay. And nothing is transmitted because transmittivity is equals to 0. Now from here I have showed you that can I write 1 minus alpha EB? I can write this, isn't it? Now, I want this body to be in thermal equilibrium. I want this body to be in thermal equilibrium, isn't it? I want this body to be in thermal equilibrium. So for this body to be in thermal equilibrium, whatever absorbed will be equal to energy emitted. Whatever absorbed will be equal to energy emitted. Otherwise, if it is not equal, then temperature will rise or decrease. So for thermal equilibrium, because it is saying thermal equilibrium, for thermal equilibrium condition, energy absorbed is equals to energy reflected. Okay. So can I say if E minus alpha EB is equals to 0? By this is reflected, this is absorbed, so it is equal, so summation is equals to 0. Or I can write this as well like this. Okay, so can I say E upon EB is equals to alpha? And what is this? What is this? Tell me very quickly, what is this? Emissivity. Yes, so emissivity will be equal to alpha. And what are the conditions for a real body? For in thermal equilibrium with its surrounding, then only you can apply this equation. Emissivity is equals to absorptivity. Okay, is it clear? I don't think I have extra space, so I have completed here. Okay, is it clear? It must be a reflected body, it must be a real body, it must be in thermal equilibrium with the surrounding, then emissivity is equals to absorptivity. Okay, let us move on. Chalo. Now next is Wien's displacement law. Wien's displacement law. Okay. What is Wien's displacement law? Look, it actually told you earlier, it also actually told you earlier that emissive power is a function of alpha and T. Alpha and T. Now, Wien's displacement actually is an extension of this. It is telling you, look, the product of emissive absolute temperature and wavelength at which emissive power is maximum is constant. At which emissive power is maximum is constant. That means wherever you are getting this maxima, here lambda max and T will remain as constant. So you see here, it will remain same. Okay, lambda max, this is lambda max here, and whatever temperature is there, it will be constant. Okay, so what can I say? It will be constant and it is equals to this, the product of absolute temperature and the wavelength at which the emissive power is maximum is constant. It will remain as constant. So can I say alpha max 1 T1 is equals to alpha max 2 T2. The product will remain same. The product will remain same. And we all know they are inversely proportional to each other. Okay. If lambda max is decreasing, then T2 will be higher. Isn't it? Look now. Here also you can see. If lambda max is decreasing, coming in this direction, higher the temperature, lower the wavelength. Higher the temperature, lower the maximum wavelength. Okay. So the ratio or the product will remain same. Okay. Max 1 upon lambda max 2 is equals to T2 by T1. This is also an important formula. First formula that we have discussed is Stephen Boltzmann's law. Second is real body in thermal equilibrium, absorptivity is equals to emissivity. And third formula is this one, lambda max 1 upon lambda max 2 is equals to T2 by T1. Okay, clear? Let's move on. Let us move on or anything. Are you not able to? Okay, chalo, ठीक है. Next is Lambert cosine law. Although I don't think any question has come from this, but still, it is a part of the law. So let us know what it is saying. It is saying the intensity of radiation in direction theta from a normal to a black emitter. It is a black emitter, okay? It is a black body. Is proportional to the cosine of angle theta. So you see here you say it is maximum, here you say it is maximum. And if you want to calculate at an angle theta, then you can find out I maximum, intensity of radiation maximum cos theta. Okay. And here at this point, what is theta? What is theta at this point? 90. So cos 90 is equals to 0. That means here I at 90 degree will be equal to 0. And I at 0 degree will be equal to 1, which is I max 1. Okay. So I theta is equals to I n cos theta. Energy radiated out decreases with increasing. As theta is increasing, as theta is going from 0 to 90, it is decreasing. Okay. And becomes 0 at theta is equals to 90. ठीक है, चलो चलो, very nice. Let us move on.
Sir,
Yes, tell me.
so basically the previous one when we were defining the range displacement law, so the relation what we
Yes,
have achieved between lambda and t. So it has been
lamp.
basically, sir, I'm not clear about it, but I think it has been derived from the Planck's black body energy distribution, right?
Yes, all the laws have been the basic for them is Wien's displacement law. All the laws are basically an extension of it.
Okay.
So all the laws are extension of it, but because it carries a very complicated C1 and C2 equation, this one, I don't know that. I mean, if you wanted that, I could have written it down, but it is a function of something C1 upon
Yes, yes, C1 and C2
uh,
to constant
C1,
and lambda
C2
power
and
5.
H, yeah, and Planck's constant and everything. So, but we do not require that. But it is for a particular wavelength. Then what did Stephen Boltzmann's law did? It basically integrated it. So that is also a
Yes.
derivation. But again, we do not. What do we need? We need these conclusions that I am giving you. Okay.
Okay, okay,
We do
sir.
not. We anyway. We will solve the question. So do not worry. When we solve the question, you will realize that is something that we do not require. And anyway, I do not think even that is covered also. But just to sometimes what I do know, that is what I am going to do in convection. Look, in convection, so many things are not required. But just to give you a flow of things, first of all, we do this, we integrate this, we get this, and then we do that. For that reason only, I have to take 3 lectures. Otherwise, for from gate perspective, it is not. I mean, even one or 1.5 class is more than enough to cover the relationships. But sometimes I have to skip because that is not at all required. Okay, and these conclusions are much more important than the equation. That equation, even if I give you no, there is really no use of it. Okay.
Okay, okay, sir.
But again, all the laws are basically extension. Planck's law basically gave that equation earlier. Then slowly, some development happened. Okay, and then you started. All the laws are basically an extension of the Planck's law.
Okay.
Hmm.
And so listen. One sir, is it like same thing what we do it here, like polarization of light, I is equals to I naught cos theta?
That I am not very sure. What are you saying? Tell me again.
Sir, basically, I was reading about one of the concept that is the polarization of light.
Hmm.
So, in that, suppose if you'll be having the light molecules in both horizontal and vertical direction, so what
Okay.
they will be, they will be one kind of a membrane. If they pass through it, so either they will hold the vertical or horizontal component, and through this they have derived the relation I equals to I naught cos square theta, where I is the intensity of the light.
Could be, yeah, could be. I really cannot comment on that. I'm really sorry. I have no idea. But I think you're talking about the optics that we study, right?
Yes, 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 right, sir, absolutely right.
So I mean, I can't just say blankly. So I am not very sure if it is a similar phenomena. Okay. But basically, we all know this, no? Like this is basically cos theta. Like whatever angle is there related to this, it is cos theta, right? This one.
Yes, sir.
This is cos theta. This is sine theta,
No, right,
right?
sir.
Hmm.
Right, sir.
So,
Because basically, what will happen? I think polarization when the radiation energy will be having in the all the direction. So they use the polarizers so that they will make it either in a vertical way or in the horizontal way to make it straight, not in all the directions. So the polarizer will hold all other directions radiations. It will cancel it out.
okay, could be, yeah. I really cannot comment on that. Okay.
Okay, 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 sir. Okay, sir.
Hmm.
Yes. Okay.
Okay.
Yes.
Chalo. Chalo. Now let us move on to the main topic that we are going to cover, and it is the most important topic that we are going to see, and it is most of the important topic for radiation as well. Not just important, it's very easy, very simple. Once you understand the concept, you see it is just like, it's actually very simple. There are very few formulas, and only those formulas are going to be used, and I am going to give you all the formulas in the concept itself, so that we will not be struggling in the question part of it. Okay, chalo, let us move on.
Sir,
Yes. Who is this?
sir, Vijay sir.
Acha, acha, tell me.
Sir, for thermodynamics and study, can you tell any book for practicing the questions, sir?
On STD, you can practice from Nag. Nag have some questions. Actually, Nag doesn't have some questions, if I remember correctly. It does not have very good questions. You give me some time. I'll take a look, and because even when I was trying to find some questions to to include in my PPTs, I don't think Nag was very helpful for unsteady. You give me some
Okay,
time. I'll take a look, and I'll give you some 10, 12 questions. Okay, I have some few questions. I'll share it with you. Okay.
okay.
But again, NSTD, you asked me, no, it is basically it's just one equation, and then you have to read out the question. It is just
Means,
one equation. Huh.
but when I study from the DS Kumar book, your it was not that equation, sir. They have directly taken only for the piping, sir. That
Uh,
filling or emptying.
No, no,
But
you
in test series,
please do not look, please do not follow that equation. Why do not follow? If the question is twisted in any way, look, I don't know if you have attended my unsteady state class. You need to know the whole equation, first of all. Then you need to understand the significance of each and every term in that equation. Okay. Knowing the
yeah, that
whole
is
equation is knowing the whole equation is important. Now if you want to remember the only filling application, then it is okay, but you cannot just rely on the filling equation or the empty equation. You must know the whole equation, you must know all the terms in that equation. ठीक है ना?
yes.
उसके बाद what is given in question, you remove the part that is not required, then come to the main thing. Okay, otherwise I would not recommend that you only know that simple equation. Okay, and filling and charging, discharging, all are the applications of that. So even, and like I'll tell you one thing, why I cannot, even if I make a summary, it is not helpful, because sometimes, for example, you are filling something and you are not emptying anything, but sometimes you are filling and you are emptying also at the same time. So the equation is going to vary on very small things that you are doing with the, with your system. So it is important that you know the whole equation. It is important that you know the meaning, what every term in that means in that equation, and then you read the question. Then you will be able to solve it. Otherwise, I don't know, on YouTube also there are some lectures of unsteady flow equation that I have taken, and some practice questions I have done. I think some 2-3 sessions you will get there at a different point of time. Maybe one I did in July or something. So you can find it out. Otherwise, I can send you the link. Okay.
Okay.
But you must have seen those lectures, isn't it? Have you attended any of those lectures?
Sir, I have attended all your lectures, sir.
Okay. ठीक है, चलो. If you know that equation, then it is good and fine. Do not worry about anything. I'll give you the question. Try to solve with the main equation. It doesn't take much. And the thing is that equation should be in your mind. You do not need to write it down for every question. You just skip all the terms that is not required. Just write the simple equation when you are solving a question. ठीक है ना?
Okay.
But if you only rely on some simplified equation, then like it will be a problem. So let's not let's discuss this later on. If you want to discuss more, let's move to the main topic. Okay.
Okay.
Chalo. So next, and very important. Okay, why I am saying it is important? I think I told you, because it is very easy. It is very easy, and question also comes, at least 1 mark or 2 mark question comes, and only based on few things that we are going to discuss, you will be able to solve your question very easily, very easily. Chalo, ठीक है. What is view factor? View factor in simple words, it is a fraction of radiation diffused from one surface element and strikes the other surface. If you have this body, okay, how much is diffused from it, whatever is coming, how much is diffused from it and reaching to the, let's say, first and second. So how much is diffused from the second and reached at the first without any intervening. Matlab, it is not disturbed by anything in between. It is directly coming at the surface. Okay, directly coming at the surface. Similarly, if something is coming here and how much it is radiating, because you see, whatever is coming, it must be diverted somewhere. For example, let's say, let me tell you one thing. Let's say something is coming here, now when some part may be absorbed, but some part may be fall here, some part maybe go like this, some part will fall here, some part will fall here, some part will fall here, some part may go like this, right? So whatever is incident here, only this fraction is called as view factor. Is it clear? Okay, because not everything that is incident, or not everything what is reflected from surface 1 will be incident on the surface 2, isn't it? This part is left, it is reflected, but this is gone somewhere, this is gone somewhere, this is gone somewhere, similarly this is gone somewhere. So only the portion that is incident on the second surface out of that is reflected from the first surface is the shape factor, 1 to 2. Okay, so F122 is direct radiation from surface 1 incident upon surface 2. So whatever radiations are going out from surface 1 and that is incident of surface 2 is F12. Now what is F21 then? What is F21? Radiation from surface what? From surface 2, yes, incident on surface 1, yes, and total radiation from surface 2. Okay, so kitna, how much have whatever has reflected or gone out or emitted, how much is directly incident on surface 2 is basically shape factor, view factor, angle factor, configuration factor, whatever you want to call it. Okay, so it is a function of geometry only. Geometry only. It is only how you have oriented, horizontal, vertical, inclined. It depends on that. Okay, it is independent of surface properties. It does not matter what is its emissivity, because it is emitted already. Whatever its emissivity, it is emitted already. Now, based upon how you have oriented your another surface, surface 2, it will depend. The view factor will depend on that. Okay, if you oriented vertically, then maybe more emitted radiations can be interfaced or incident on the second surface. If it is placed horizontal, then very few incident radiations will received by surface 2. Okay, so only depends on the, again it is independent of the surface temperature, because surface temperature will determine how much radiations are going out. But how much it is going to, once it has gone out, then how much is received by surface 2 it is independent of properties and surface temperature. Is it clear? So it is Q12, and how much is radiated? How much is radiated, bhaiya? Radiated is absorptivity A1 T1 to the power 4. Okay. It is basically, you see, it is emissive power F12 Q12 upon A1 E emissive power. Okay, so it is Q12 A1 sigma T1 to the power 4. So from here, you can find out the heat transfer from 1 to 2. It is A1 F12 sigma T1 ki power 4. It is in, what is the unit? What is the unit? Watts. Yes, very nice. Chalo. Now, very, very, very important rules that we need to follow. Rules that we need to follow. Okay. So,
Hello, sir.
yes, tell me.
So here, if you take an example, if the body 1 and body 2 both are like emitters, both will be emitting the radiation. So body 2 will also be emitting the radiation.
Yes.
And the
But
body
it
2
is...
radiation.
Okay. Tell me. First of all.
Body 2 radiation will fall on surface 1. So definitely there will be some proportion of the light which will get reflected back, and which will be again falling on 2.
Then
So
you need to
like,
subtract it. Then this will be talked about tomorrow. Then it will be
because
subtracted.
then sir,
Q1 to...
the total emission from 1 to 2 will be the net radiation emitted from 1 plus the radiation which reflected back, which has been released from 2.
So it will be let's say A1 F12 sigma, for example, T1 ki power 4,
Yes,
and
sir.
whatever is 1 to 2, whatever is reflected back. So it
Yes,
depends
sir.
on
Where
that.
we can take that reflectivity constant. So with that, we'll also get
Whatever
okay.
by कितना reflect करेगा वो, it depends on T2 की power 4.
Yes,
And
T to the
this,
power 4 and reflectivity constant rho.
yes.
Yes, sir. So it will be like same F21 sigma rho T to the power 4 into area.
ठीक है. So this is reflected, this is absorbed. ठीक है ना?
Right.
हाँ, चलो.
Okay, sir.
So reciprocity rule. क्या कहता है? What does reciprocity rule means? It simply means, again I'll write this equation. Let us talk about what is the net heat transfer from 1 to 2. If 1 to 2 by Q1 to 2, similar equation let's write. कितना heat transfer? What is the heat transfer from 1 to 2? By heat transfer from 1 to 2 will be A1 F12 sigma T1 की power 4. Okay, whatever the temperature is, it is going to reflect that out based on that. Okay, and it will be absorbing also something, and that will be A2 F21, okay, sigma T to the power 4. Whatever is reflected from here, some portion will be absorbed by surface or the body 1. Okay? F21 is telling you how much is, what is F21 telling you? What is F21 is telling you? Look, A2 sigma T to the power 4 is what? What is this? This is energy emitted by body, energy emitted by body 2. But if you're going to multiply this by F21, it is going to tell you the fraction absorbed by body 1 out of the total radiated out from the radiation from 2 incident on 1. Yes, that is correct. So that is why it is what is absorbed from 2, and that is what reflected from, it has gone out. This is the energy that has gone out from 1. Okay, it is energy out from 1, it is energy absorbed by 1. ठीक है, clear? Okay, chalo, if it is clear, and I am assuming thermal equilibrium. So net heat transfer will be 0. Net heat transfer, nothing is going out. Net heat transfer is equals to 0. Okay, and thermal equilibrium is there. So T1 is equals to T2 is equals to T. Okay, so I can write 0 is equals to A1 F12 minus A2 F21 sigma T to the power 4. ठीक है, चलो. Now it will go on the other side. I can write A1 F12 is equals to A2 F21. Okay, and this is, yes, very nice. Sahil is correct. This is your A1 F12, A2 F21. Okay, so this is your reciprocity rule. Reciprocity rule, and very important rule. You are going to use that in every question. Every question you are going to use this. And not, let's say that is exaggeration of it, but let's say more than 95% of the questions you are going to use it. Okay, clear? Chalo, let us move on to the next part. Summation rule. Summation rule you can say, or you can also say conservation rule or enclosure rule, whatever you want to call it. Okay, the sum of view factors from surface of an enclosure to the surface, if it is an enclosure, right? It is an enclosure. So let's say we are talking about this surface 1. This surface, okay, including to itself must be equal to 0. So for example, in general, I can write Fi to j, summation of all the radiation from I to j, where j is varying from 1 to n. Now what is n? N is 2, 3, 4, 5, from 1 to n. So I can write, and it is saying it is equals to 1, which is also equals to F11 plus F12 plus F23 plus F, one second, 1 to 2, 1 to 3, 1 to 4 plus 1 to 5. Okay, so this is your summation rule. If only two surfaces are there, then for example only two surfaces are there, this and this, so I can say F11, this is 1, this is 2, F11 plus F12 is equals to 1. Okay, I can also say F21 plus F22 is equals to 1. Any doubt in this? Only two surfaces are there. And बहुत ज़्यादा, very frequently we are going to use this formula as well. So reciprocity and summation rule are very, 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 very important. Okay, chalo, next rule. superposition rule. Superposition. For example, this is a body I and this is the body F. This is the whole body F. Whole body F. Okay. So superposition or associative rule tells you that shape factor of I to F, shape factor of I to F is equals to shape factor of I to J plus I to K. For example, I can say F 1 to 3, 1 to 1 to 4. If this is 1, this is whole 4, and this is 2, this is 3. Okay, F1 to 4 is equals to F1 to 2 plus F1 to 3. By whatever is coming here, either it will go here or it will go here, isn't it? It will not go anywhere. Okay, chalo. That is third. Fourth is symmetry rule. If two identical surfaces are oriented in the symmetry with respect to another. Okay, if two identical surfaces, for example, one is a surface and two identical, 2 and 3 are oriented in symmetry with body 1, okay, then it will intercept identical amount of radiation leaving the surface. So I can say whatever is leaving from 1 and reaching at 2 will be equal to whatever is leaving from 1 and reaching at 3. I can write this. Is it clear? Okay, very nice. Chalo, so up we have covered 3 parts. What are the 3 parts? Terminology, radiation heat transfer laws, and fourth is rules. Now let us come to view factor, main concept. Although these rules are very, very important to calculate view factor. Okay. And then we will go to numericals, last portion. If even we delay some time in the lecture, please be with me. Do not go because it is a very important topic. Okay. Maybe we can extend it for some time, 10-15 minutes. Just be with me. Or maybe not. I'm not sure. Let's see. Chalo. So tell me, if you have a flat surface, that is surface 1. So if I need to calculate F11, how much will be F11? Can you tell me? Surface, radiation leaving from surface 1 and reaching at surface 1. 0. Yes, very nice. It is equals to 0. Very nice. Now tell me, if it is a convex surface, let's say this is your 1. Now how much is F11? Yes, very nice, very nice. Okay, concave surface, how much is F11? How much is F11? I'm waiting for you people. 0 to 1. Yes, it is non-zero. Its value can lie. It will not be 1, of course, because it is open. Okay. But it will be greater than 0. It will be greater than 0. Of course, it will be greater than 0. It is not equal to 0. Yes, it is non-zero. Okay. Chalo. If we have a concentric cylinder, and I say that is body 1 and outer one is body 2. So tell me, if I say F11, how much will be F11? Look, this is going this. Look, there is one assumption that we assume here. We assume that very long cylinder. Okay. Look, the body 1 will be radiating energy from here. Everywhere it is radiating energy. It is radiating energy from the surface. It is also radiating energy from the circumference, outer circumference, this one. Okay. Now tell me how much is F11? How much is F11? Yes, F11 is equals to 0. But why? Why is it 0? There are certain radiations that are going out. You see, It is not. Okay, 1 1 will be 0. Yes, 1 1 will be 0. 1 1 will be 0. Okay, nothing is reaching at 1 again. Okay, but and I can add summation rule. So f11 plus f12 is equals to 1. Now this is 0. f12 is equals to 1. Okay. Now we can see here that not all the radiations that are leaving surface 1 is reaching surface 2, isn't it? There are some radiations that are lost here and here. Okay, but that is why we are assuming that it is a very long cylinder. It means the radiation that are lost from the circumference, from the outside, okay, from this is basically negligible compared to the length of the cylinder. Okay, it is very less, very, very less. Okay, so that is why f12 can be assumed as 1. F12 can be assumed as 1. Okay, also if you can also do something, you can also find out what by a1 f12 is equals to a2 f21. Okay, हमें क्या what this equation is saying that radiations that are leaving surface 1 is absolutely reaching, all the radiations are reaching at surface 2, but then using reciprocity rule I can find out f21 is equals to a1 by a2, right? I can also find out again, I can use summation rule. I can say that f21 plus f22 is equals to 1. So I can find out f22 is equals to 1 minus f21. Okay, so all the 4 values I can find out. Is it clear? Let me drink some water and then we will start. Is it clear? Chalo, very nice. Let's move on. Concentric cylinder, concentric sphere, I am sorry. One sphere is enclosed by a bigger sphere. This one small sphere with radius r1 is enclosed by a bigger sphere r2, completely enclosed. So I can say f11 is equals to 0 and f11 plus f12 is equals to 1. That means f12 is equals to 1. And again, then we can find out based on the reciprocity rule and summation rule f21 and f22. Okay? Do I need to do it again? Okay, chalo, let us move on. Now this is a long triangular duct. Okay, it is a duct. It is, like this. Moving, it's a long triangular duct. So you need to find out certain things, but tell me one thing. What is F11? Yes, it is 0. Tell me what is F22? Yes, whenever plane surface is there, then radiation emitted from that plane surface and radiation received by itself is always equal to 0. 3 is equals to 0. Okay, I can then again use f11 plus f12 plus f13 is equals to 1. I can also use f21 plus f22 plus f23 is equals to 1. I can use f31 f32 plus f33 is equals to 1. Okay, I can use reciprocity rules as well. Now we know this is 0. We know f22 is 0. f33 is 0. Okay, so using all these formulas, we can further calculate our whatever they are asking in question. Okay, chalo. And the last part. So if it is a long symmetrical wedge, then F12, how much is leaving 1 and reaching 2 can be calculated, or F21 also can be calculated as 1 minus sine alpha by 2. Only one question have been asked till now on this type of problem. That's why I have included this in the concept. Okay, is it clear? Is it clear? Chalo. Now let us come to the final part of our lecture, which is questions. Let's try to do the questions and see if the concept that we have covered are enough to solve the questions or not. And then look, I would not recommend you solve all the questions because some of the concept, and again one of the important concept is still remaining for tomorrow. It's still remaining for tomorrow. So maybe in some editions questions you will find difficulty, but do not worry about it. In fact, all the view factor questions I have already taken here. Okay, chalo. Bhaiya, opaque body, very nice. Already answer is there. Because we know transmissivity is equals to 0, and I know alpha plus rho plus tau is equals to 1. So this is 0. Alpha plus rho is equals to 1. Very nice. Already answered. Very nice. Chalo. Let us move on to the question. A solid cylinder is located at the center of a hollow sphere. By one cylinder is there. Okay. And it is centered at the center of a sphere. Now sphere is surface 1 and cylinder is surface 2. Okay. Diameter of the sphere is 1 meter. So what is radius of 1 is equals to 0.5 meter, while the cylinder has a diameter and length. So R2 is 0.25 meter and L2 is equals to 0.5 meter. The radiation configuration F11 I need to find out. F11 I need to find out. Now you tell me. Bye. Tell me first of all, F22. How much is F22? F22. Yes, F22 is 0. Okay. Then by using summation rule, it is summation rule, right? Yes. By using summation rule, can I say F21 plus F22 is equals to 1? So can I say F21 is equals to 1? Any problem? Anybody? Now let me apply reciprocity. Let me apply summation rule for body 1 hai ye, for body 1. So I'm sorry, for body 2. This summation rule for body 2. Okay. Summation rule is only applied to one body. Okay. F21 plus F22. ठीक है. Reciprocity rule let me apply between 1 and 2. Now you can apply that between two bodies. Okay. So A1 F12 is equals to A2 F21. Okay. So F12, can I find out A2 by A1? A2 by A1 can I find out? C is the answer, 0.75 you are saying, but I do not think that is correct. Let us check. Yes, 0.625 is correct. Very nice, Sai. What mistake you have done, Sai? Hello. A2 is what? A2 is the area of cylinder. Okay. And A1 is area of sphere. So we all know what is area of cylinder. by circumference area 2 pi r square, या pi d you can say. Okay, and then 2 pi r h. Okay, and sphere is what? What is the area of sphere? Anyone? Sahil has already solved it. 4 pi r square. Now this is R1, this is R2, this is R2, and this is L2. This is L2. Okay. So yes, 4 pi r square. Very nice. So you can put the values, you know everything, and calculate F12. Calculate F12. How much is F12? Can you tell me, Sahil, how much is F12? It is 3.3 by 8. Let me check. Yes, it is 0. Why did you? It is inside the body, right? It is not two concentric cylinders. It is inside the body. The whole cylinder is enclosed by a sphere. ठीक है साइन? चलो. So it is Sahil is telling 3 by 8, which is 0.375. Now let me apply summation rule for body 1. Summation rule for body 1. So can I say F11 plus F12 is equals to 1. So we need to find out F11 is equals to 1 minus F12. And how much is F12? 0.375. And Sahil and Sean has calculated wrong. Sahil, acha, Sean, what is the answer? 0.625 is F11. Clear? Yes. Yes, Sean, that is correct. Chalo, this is your first question. I do not need this. Let's move on. A hollow enclosure is formed between two infinitely long concentric cylinder. Okay. So in concentric, you may neglect the area outside. Okay. Chalo. Two infinitely long concentric cylinder of radii R1, surface 1. So this is R1. This is R2. Okay. So R1 is equals to 1 meter. R2 is equals to 10 meter. Radiative heat exchange takes place between the inner surface and the larger surface and the outer surface of the smaller cylinder. Okay, so it is saying only here it is radiating. Okay, inner surface of the, that means this one, inner surface of the outer radius and outer surface of the inner radius. That means there is no radiation. 1 second, I'm sorry. That means there is no radiation either here or here. Okay, chalo. The radiating surface are diffuse and the medium in the enclosure is not participating. Means if whatever medium is there inside the surface, it is not participating. Okay, the fraction of thermal radiation leaving the larger surface and striking itself. So what I need to find out, can you tell me what is they are asking in the question? Larger surface, Sahil. Sean is wrong. Yes, Sahil is correct. Larger surface. Which one is larger surface? Yes, F22 I need to find out. F22. So भैया हमें तो पहले ही पता है F11. That is why it is very important to mark the surface ahead. Okay, before solving the question, mark at least, if it is not given in question, then mark yourself surface 1 and surface 2. Then write all the notations based upon your surfaces. Okay, so F11 is equals to 0. And from summation rule, by surface 1, I can say F11 plus F12 is equals to 1. That means F12 is equals to 1. Okay. Now I can apply reciprocity. Reciprocity rule. What is reciprocity rule? A1 F12 is equals to A2 F21. Right. Now F21 will be equal to A1 by A2. So this is 2 pi R1L, 2 pi R2L. Everything will be cancelled because R1 by R2, 1 by 2, 0.5. And I do not need F21, I need F22. So I can apply summation rule for body 2 F21 plus F22 is equals to 1, and that means F22 is equals to 1 minus F21, which is 0.5, and that means it is 0.5. B is the correct answer. Everyone has already solved it. Very nice. Thank you. Clear? Clear. Chalo, let us move on to the next question. GATE 2008 2-mark question. Next question. GATE 2000.
So,
Yes. Yes.
sir, when will you take the convention part, sir?
You can no, look, unless it is not given in question, then please don't. Whatever is given in question, take those conventions. If not given in
No, I
question,
am
then
not.
you can take. Okay.
It
Tell me,
was
tell me.
a topic, sir. Topic. I am asking for the topic.
Okay. Convection.
Yeah.
What are you saying? Just ask again. I'm sorry.
Convection topic, sir. There was external flows, internal flows was there. That topics when will
Convection.
be
Are
there?
you asking when I covered that topic, right? That is what you are
Yeah.
asking.
Yeah.
I'll cover that. We have 2 lectures of radiation, then I'll come to convection.
Okay.
Okay. Chalo. So next lecture be of radiation, and then we will start convection. We will take around 2.5. 2 mein to it will not be over, but around 2.5, 3 lectures we will finish it. Okay. Although 3 next lectures are not, chalo koi nahi, we'll see that. Chalo, next question. GATE 2012 2-mark question. 2-mark question. Consider 2 infinitely long thin concentric tubes of circular cross section as shown in figure. They have already given us surfaces. They have already given us surfaces. This is 1 second. Yeah, what is this? Okay, this is 1 and outer is 2. So it is saying it is D1 and it is D2 are the diameter of inner and outer tube. View factor F22. F22. Of course, we just calculated F22, which was equals to 1 minus F21. और F21 कितना था भाई A1 by A2, और इसको हम ऐसे लिख सकते हैं D1 by D2 or R1 by R2. So D is the correct answer. Very nice. Same as previous question. Yes, it is same as previous question. Very nice. Okay, chalo. And it is 2-mark question. You see here. That's why I'm saying view factor is a topic that if the question comes also very frequently, you will get the questions. So if the question comes, those 2 marks must be with you. Okay, you cannot miss. Yes, that's what. No, look, because we have done this question right away, that's why we just got the answer. But sometimes, look, if you have solved, and whenever you are in exam, that time you have not just revised radiation or even heat transfer, you have revised 16 subjects or let's say 12 subjects. So it's very, it's not very obvious that it will come directly to your mind. Maybe you will solve it, you don't put the values but you solve it, so it may take some time. Okay, that's why. But yeah, I mean, it is a question, if you have done enough practice, then you even remember it by heart. Okay, it depends on in person to person. Okay, chalo, let us move on. For a circular tube of equal length and diameter, L is equals to D here. the view factor F13. Look, this is 1, this is 2, and this is 3. F13 is given to me. F13 is equals to 0.17. I need to find out F12. I need to find out F12. Okay. So because we are all, look, it is 13, it is 12. That means we are talking about surface 1. So summation rule, summation rule for first surface. Can I write F11 plus F12 plus F13 is equals to 1? Can I say that by 1 say 2, 1 say 3, and 1 say 1? No, there is nothing 1 to 1, right? So F11 we all know will be 0 by plane surface is there. And F13 is given to me. So F12 is equals to 1 minus F11, 13. Okay. F12 is equals to 1 minus 0.17. That means is equals to 0.80. Look, this is also 2-mark question. Not more than 15 seconds it must take to solve this question. 2-mark question. Okay. 0.83. Also, but you must also know that what is F33? Tell me, what is F33? Just in case something else comes in question. F33. Yes. Can you tell me how much is F22? Yeah, it is not equal to 0. It is not a plane surface. Okay. Tell me.
Sir, I think you are taking the wrong notation, sir. I think I have one was the cylinder, sir. 2 and 3 are circular discs.
It is a plane surface. No, Baba, it is a hemispherical. Like, for example, you have a tube. No, look, this is given A2. This is given A3. So what I am taking?
Okay. Means yesterday only I have solved another notation of this. They
It
have
could be
taken
different
the
question, na, Baba? It could be different question, isn't it? They have given this is
Okay.
A1. That means it is surface 1. It is A2. That means it is surface 2. It is A3 surface 3, isn't it? Okay. Or maybe you have solved a question in which they have changed the surface. Hai. Could be.
I didn't see that surface notation, sir, actually.
अच्छा कोई बात नहीं. Okay, so A22 is not equal to 0 because there could be certain radiations from surface 2 that can fall on 1, of course, that can fall on 3, of course, but there will be some radiation that will fall on 2 also. So F22 is not equal to 0. Clear? Clear, everyone? Let's move on. F22 is equals to by 2. What are you doing? Look, if I talk about 2, then if it will be F21 plus F22. हाँ बताओ.
Sir, like in the case of surface 2, can we consider like symmetric rule? Like the
Can we
radiation
consider what?
Symmetric rule. Like
Symmetry.
we see that
Symmetry you can consider. No. You cannot consider actually. Look, if you can consider symmetry, if this is a plane surface, and then this is happening, then you can consider plane surface. Okay, but because some is falling here as well, no. So it is not divided. Whatever is leaving 2 is not divided in 1 and 3. It is also divided in 2 as well, isn't it? You can only consider symmetry when whatever is leaving 2 is only falling on 1 and 3, isn't it? Chalo. Let's move on. Next question. A solid sphere of radius R1. Look, in mostly question they will give you the notations. If they are not giving, then you can take anything. Okay. Chalo, inner is 1, outer is 2. Okay. R1 is 20 and R2 is 30 as shown in the figure. The view factor F21 I need to find out. I know that you can find out before me, so solve it very quickly and tell me what is the right answer. By F11 is equals to 0, F1 to 2, that is correct. No, what is YD? Just check your answer. F11 plus F12 is equals to 1. Okay, A and B are basically same, isn't it? ठीक है साहिल, no problem. Okay, so A and B seems to be the same option, isn't it? F12 is equals to 1. YA, how are you getting AR? Check again. Check again. Yes. So what is the answer now? Yes, B is the answer. Of course, B is the answer. Okay. Chalo. This is summation rule for body 1. Then we can apply reciprocity rule. So A1 F1 2 is equals to A2 F21. F21 I need to calculate A1 by A2, and this is 4 pi R1 square, 4 pi R2 square, R1 square by R2 square. That means 20 square by 30 square. So it will be 4 by 9. Yes. ठीक है. Chalo, let's move on to the next question. A solid sphere of 1, solid sphere 1, that is 1, okay, of radius r is placed inside a hollow closed hemispherical surface 2 of radius 4. The shape factor F21. F21 I need to calculate. F21 I need to calculate. And we will apply the same thing and we will get A1 by A2, isn't it? Or do I need to do everything again? Do I need to do everything again? By F11 is equals to 0. So F12 will be equal to 1. Then apply reciprocity. A1 F12 is equals to A2 F21. So F21 is equals to A1 by A2. ठीक है? Now A1 and A2. What is A1? A1 is a sphere. A1 is a sphere. So can I say 4 pi R1 square? Yes, that is true. Sahil is correct. A is the correct answer. What about a hemisphere? Hemisphere. Tell me, what about a hemisphere? What is the area for a hemisphere? Yes, that is pi r square plus 2 pi r square. That is 3 pi r2 square. Okay. Now you know everything. R1 is how much? Pi and pi will be get cancelled. R1 is simple r square and R2 is 4. So 4r square. Okay. That is 4r square upon 3 into 16 r square. R and r will be get cancelled. 4, and that is 1 by 12. Very nice. Very nice. Chalo, let us move on to the next question. The peak wavelength of radiation emitted by the black body at temperature So this is T1 and this is lambda max 1. Okay, peak wavelength means maximum wavelength. If the peak wavelength of emitted radiation changes to, that means maximum 2, then I need to find out T2. Can you find this out? Can you find this out? Yes, Sean and Sahil both are correct. It is by, I know lambda max into T is equals to constant. So lambda max 1 T1 is equals to lambda max 2 T2. I need to find out T2. So lambda max 1 upon lambda max 2 into T1. Lambda max 1 is 1.45. It is 2.90. It is 2000. This is 2. This is 1000. And this is 1000 Kelvin. Clear? Chalo, let us move on to the next question. Sphere 1 with a diameter 0.1 is completely enclosed by another surface sphere 2 of diameter. So this is 0.1 meter and it is completely enclosed by diameter 0.2 meter. Okay. Yes, very nice. I can already see the answer. So this is 0.5 meter R1, R2. The view factor 1 F12. Arey yaar, we already know F11 is equals to 0 and F11 plus F12 is equals to 1. F12 is equals to 1. It is a 1 mark question. GATE 2019, you see. Very recent question. Yes, yes. Very nice. Chalo. Next question. The spectral distribution of radiation T1 is given has maximum wavelength lambda max. The body cools down to temperature T2. If the wavelength corresponding to maximum of the spectral distribution T2, so it is saying lambda max 2 is equals to 1.2 times of lambda max 1. T1 is given, T2 I need to find out. Find out very quickly by lambda max 1. T1 is equals to lambda max 2. T2. T2 is equals to lambda max 1 lambda max 2 into T1. So it is 1 upon 1.2 into 3000 T2. So what is the answer? 2500. Very nice. Very nice. Okay. GATE 2022 mark question. You see here, it is a very recent question of 2 marks. Nothing, not more than 20 seconds it must take. All these formulas you don't need to write. You need to directly write this. Okay. Directly put the values and solve it. I have to write because I need to write it. Otherwise, it is not required. Let us come to the last question for today. Okay. A solid sphere of radius is there of radius 10 millimeter is placed at the centroid of a hollow cubical enclosure. It's a cube enclosure of side 30. This is 30. This is 30. This is also 30. The outer surface of the sphere is donated by 1. This surface is donated by 1. And the inner surface is donated by 2. This is 2. The view factor F22 I need to find out? F22 I need to find out. Very simple, very simple. By F11 is equals to 0. F12 is equals to 1. Reciprocity, A1 F12 is equals to A2 F21. So F21 is equals to A1 by A2. Okay. Then summation rule for body 2. क्या? F21 plus F22 is equals to 1. F22 is equals to 1 minus F21 is equals to 1 minus A1 by A2. What is A1? What is A1? It is 4 pi r square. What is A2? What is A2? 6 into area of one side. There are 6 sides, area of one side. So this is L square. L square. Okay. So you can put the values. भाई ये R1 है. 1 minus 4 pi. R1 कितना है आपका? 10 millimeter. So 10 square upon 6 into 30 square. And the answer that Sai, Sean, and Sahil have already gotten is F22 is equals to 0.767 or 77. They are asking up to 2 decimal places. This is the answer. GATE 2021 2-mark question. You see. So ऐसा नहीं है that they are adding anything in this. It is view factor that is very. You see, we have not solved any question on Stephen Boltzmann's law, on any other thing, but view factor is very. So many questions every year. 2021 is there. I think even 2022 they have asked something. I have to check it again. 20 they have asked the question. 19 they have asked the question. 18 they have asked the question. 15 they have asked the question. 14 they have asked the question. And I may have left few questions. 12 they have asked the question. So almost every year they are asking questions. 12, 5, almost every year they are asking questions from view factor. And you see how easy it is. If you have understood what we have done, if you know these few rules, then it is more than enough. Okay. Are you happy? Are you happy with today's lecture or not? Tell me. Chalo, ठीक है. I am also very hungry now. Okay, it's a very odd time today at class. You are not, like you are in the middle of your dinner time. Chalo, ठीक है. So now we are left with 3 lectures. Okay, but just to review what we have done today, we have done some terminology in which we have talked about absorptivity, reflexivity, transmissivity. Okay, black body, gray body. Okay, emissive power of black body, total hemispherical power, and all these things. Then we have talked about laws. Okay, laws, radiation laws, Planck's law, Stephen Boltzmann's law, okay, Wien's displacement law, and Lambert law. Okay. Then we have talked about rules. What are the rules? Can you tell me? What are the rules? Reciprocity, summation. What else? Symmetry. What else? Wedge, no, wedge was not the rule. It was just some example of that view factor. One rule was also there. I forgot the name. Just let me check. Superposition. Yes, superposition. Superposition. Okay. And then we have come to view factor of, we have seen certain surfaces we have seen, and bodies we have seen. If one body is enclosed, if a cylinder is enclosed, if a sphere is enclosed, okay, that we have seen. And finally, numerical we have done. And I hope that whatever we have covered, the concept we have covered is more than enough to solve all the questions. Now you can go back, although radiation we have already solved all the view factor questions, maybe one or two you can get, but you can see other questions in the book and try to solve it. Otherwise, we will cover whatever is left of radiation in the next class, and then you will be able to solve any workbook, any practice questions for radiation. Okay? Chalo. So I hope this is enough for today, and we will meet tomorrow. And next time we will know. I don't know what day, but let's see. I mean, I'm not sure. So you will get to know. I'll also get to know, and we will meet the next. Okay? Chalo. I'll see you soon. Tata, bye bye. Thank you so much. Chalo, I'm going to end the session. I'll see you later. Bye bye.